Section 10.6, binomial expansion theorem and Pascal's triangle. Well, let's begin with the word binomial. What is a binomial? Let's say, here's the easiest binomial I could think of, a plus b. That's two terms. That's what we call a binomial. Now they're saying expansion, all right? So, and a theorem means the truth. So what is the truth about expanding a binomial? Well, right here you can't really expand it yet, but let's say I told you, take that a plus b binomial and let's have it raised to the third power. So right here you could expand it. What does that mean? Well, do the math. What does the third power mean? That you're going to multiply this binomial with itself 3 times. So let me do that. Then after that, of course, we need to start multiplying. So if I take this a times a, we're going to get an a squared. If I take the a times b, we're going to get an ab. If I take this b times a, we're going to get a positive ba, but I'm going to write it as ab. Always write it in alphabetical order. And then positive b times positive b is positive b squared. And of course, we could combine the middle two terms, a plus b and a plus, or not, ab plus ab. We could actually combine those. And if we combine one ab plus another ab, we're going to get a total of 2 ab's, and it's positive. Let's bring down the a squared in the front. Let's bring down the positive b squared at the back. So what we have here is the multiplication of these two binomials gave us this quadratic trinomial, and we still need to multiply by this other binomial. So I still need to take this and multiply it by this positive ab over here, or binomial ab. So let's show the work right here. We're going to take the a times a squared, that's going to be an a to the third, a times 2ab, that's going to be a positive 2a squared b, and then b times, no, I'm sorry, a times the final term right there on the trinomial b squared, it's going to be a positive ab squared. And then we have to distribute the b, okay? So let's take the b right here and distribute it. B times a squared, that's going to be a positive a squared b. And then how about b times 2ab? That's going to be a positive 2ab squared. And b times b squared, that is b to the third. Now we still need to combine any terms that we could actually combine. And as you see here, there are no terms that are alike. We have a 2ab squared, but we don't have any other ab. Oh, we do have an ab squared. It's right here. So let's take this 2ab squared and combine it with this ab squared. So when I do that, show my work, this positive ab squared with that positive 2ab squared will give us 3 of those ab squares. What else do we have? Oh yeah, we also have this positive 2a squared b with this positive a squared b. So that would be positive 3a squared b, right? You just combine them. And what else? Nothing else combines, so let's bring down the a to the third in the front, a to the third, and bring down the plus b to the third at the end. Okay, ladies and gentlemen, this is our answer right here when we expand this binomial to the third power. Now, that was a lot of work, right? Now, it gets even more challenging if we had like a number 2, like 2a plus 3b, or 7a minus 18b. I don't know. It could get way more challenging. And what makes it even more challenging, imagine if this was to the 4th power, then I'd have to multiply this giant, you know what, I forgot the plus sign. That was a positive 3ab squared. I'd have to take this 4-term polynomial and multiply. If it was to the 4th power, I need to take another ab and multiply it over here, ab times this, which would even take up like an entire piece of paper. So as you could see, this is ridiculous to expand a binomial with distributive property. Is there an easier way? Absolutely. As a matter of fact, this is what I want to do. I want to do the same problem over again with the shortcut that I'm about to teach you. But what I am going to do is cut this answer out and duplicate it, move it over here, and I will take this answer and save it. That way we could compare it. So let's begin. Again, I'm saving this answer right here for later. Let me just push to the side. We're going to check that out later. Let's begin by understanding Pascal's triangle. Pascal was a mathematician, and he came up with this triangle. So let's make a triangle of ones. Put a 1, and a 1. right? It's a triangle of ones. And what you do to make this triangle greater, you take this number and this number, and you add them together and you put your answer right here. So 1 plus 1 is 2. Let's put the 2 right here. And what do we do after we get that answer? We put ones on the outside again. Okay, so it maintains the triangle, right? So that's called a Pascal's triangle. Again, get this 1 and this 2 and add them together and put the answer right here in between, but a little bit below on the next row. So 1 plus 2 is 3. 1 plus 2 is 3. And once you do the addition, what do? You put ones on the outside again to maintain the triangle. Now let's keep going here. We have 1 plus 3. That's going to give us a 4. So let's put the 4 right here. The 3 plus 3 gives us a 6. 3 plus 1 gives us a 4. And once again, we put ones on the outside. And we could continue this triangle forever, right? Quickly, 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. Put ones on the outside again. Ladies and gentlemen, this right here is what we call Pascal's triangle. I know you're thinking, okay, I know how to make it. Just simply add them together, and you'll get the answer there. 1 plus 1 is 2. 2 plus 1 is 3. Keep putting ones on the outside. Ones on the outside. Simple, right? 4 plus 6 is 10. Easy peasy lemon squeezy. Question is, who the heck cares, right? Why do we need this triangle? Well, this triangle will help you expand a binomial without doing that much of the crazy work that we just did at the beginning 5 minutes of this video. So let me show you how this triangle works. Let me move this triangle over here. And it's this simple. Over here, we're going to write the word power. I would like you guys to follow along in your notes. Now, anything to the power of 0, anything to the power of 0 is 1, right? On the calculator, if you go 5 to the power of 0, your answer is 1. Now, anything to the power of 1, let's say we have a binomial to the power of 1, then you're going to end up with 2 terms. That's why we have a 1 and a 1. So this triangle ultimately becomes the coefficients of your terms in your answer depending on the power of your binomial that you need to expand. So we have the power of 2, we're going to be using this row. Power of 3, we're going to be using this row. Power of 4, going to be using this row. Power of 5, you're going to be using this row. Okay, so this is something you need to understand. You need to be able to create this triangle on your own. You need to be able to understand anything to the power of 0 is 1. Power of 1 gives you these coefficients on your 2 terms of your binomial. Power of 2, so on and so on and so on. So we just did the example a plus b to the 3rd power. Okay, so let's do this example over again, but using these notes. So a plus b to the 3rd power, that would imply that we go down to the power of 3, and our answers are going to have the leading coefficients, or the coefficients of 1, 3, 3, and 1 on each of our terms. Okay, so knowing that I have a binomial to the 3rd power, I could take these numbers and rewrite them, followed by 2 parentheses on each term. Okay, so what do I mean by that? I want to take the 1, 3, 3, 1. Okay, I want to take this 1, 3, 3, 1, and I'm going to write it right here. 1, but I am going to put parenthesis, parenthesis, and then plus 3, parenthesis, parenthesis, plus 3, parenthesis, parenthesis, plus 1, parenthesis, parenthesis. This is the setup, guys. Once you know your binomial, once you know the power of that binomial, you go to that certain power on Pascal's triangle, you write down the numbers 1, 3, 3, 1, followed by 2 parentheses on each one, right? 1 parenthesis, parenthesis, 3 parenthesis, parenthesis, plus 3 parenthesis, parenthesis, plus 1 parenthesis, parenthesis. That's exactly what I have here. Now, what do you think we're going to be putting in this first parenthesis? The first term on your binomial. That a goes right here, and it also goes on the first parenthesis of each term. The a goes on the first parenthesis of each term. There you go. And that was simply just taking whatever number is there or term is there and just put it right there. If this would have been a 2x, you'd put in a 2x right here and right there and right there and right there. If this was a 7z, you'd put a 7z right there, right there, right there. You put this first term of your binomial, put it in the first parenthesis of each term. Okay. Now, how about this second term of the binomial? Like if that was a minus 7y, then you'd put a minus 7y here, a minus 7y there, minus 7y there, but it happens to be a b. All right, so let's just put a nice simple b in all those second parentheses. Pretty simple, right? Now, what's missing here? We're obviously missing the exponent 3. So this is the trick that you guys need to understand. The trick is, on your first parenthesis, you need a power, and that will be this maximum power of 3. So let's put the maximum power of 3 right there, okay? Now, if you're multiplying, you really add exponents. So what exponent must be up here if the highest power is 3? It must be a 0. So you put your max power on your first parenthesis, which makes the second parenthesis power a 0. And then the trick is that the first power on the first parenthesis drops down by 1 as the second one increases by 1, giving you the total power when you add them to be 3. So this 3 is going to drop to a 2. And then this 0 is going to increase to a 1. You see that? So this 3 dropped to a 2, the 0 increased to a 1. And that makes total sense because when you multiply two terms, you add exponents. 3 plus 0 is 3, 2 plus 1 is 3. So this next one, what's going to be right here? Well, the 3 dropped to a 2, it's going to drop to a 1. Okay, so you put a 1 right there. And the second parenthesis exponent, the 0, went up to a 1, it goes up to a 2. And finally, last but not least, the 1 on the first parenthesis is going to drop to a 0. And the b, or the power on the third parenthesis, the 2, goes up to a 3. So I know this is really confusing. It's the first time you see it. You just got to get used to the way this works. This is a binomial expansion theorem, okay? So you need to first know Pascal's triangle, how to create it. Pretty straightforward the way I explained it. And then after that, you set up these numbers followed by two parentheses, so you could put both of your terms of your binomial in each of those parentheses, right? Again, if this was a 3x, you'd have a 3x here. If this was a minus 7y, you'd have a minus 7y right there. But it's a nice simple a and b in this case, so you put them right there. And then you need the power of 3, that max power of 3, you put it on the first parenthesis. And this drops to a 2 on the next first parenthesis. It drops to a 1 on the next first parenthesis, and it drops to a 0 on the last first parenthesis. And then the second parenthesis from 0 increases to a 1, it increases to a 2, it increases to a 3. So this max power and this 0 power, they trade places, right? The 3 drops to a 2 as a 0 increases to a 1, drops to a 1, increases to a 2, drops to a 0, increases to a 3. I hope that makes sense. That's the theorem. That's what you need to know how to do. Now, after that, you just need to do your work, right? So what is the work here? What's b to the 0? B to the 0 is 1, so you could just scratch that out. It's not there. And what is 1 times a to the third power? Well, that would be a to the third power. Okay. Now, keep in mind, if this would have been a 2x, then you'd have to go 2x times 2x times 2x, because it's to the third power. You'd end up with 8x to the third. Over here, we end up with 3 times a to the second. That's just 3a to the second times b to the 1. So it's just going to be 3a to the second b. So you really have plus 3a to the second b. And over here, we have, again, 3 times a to the 1. That's just 3a. And then b squared, that's just 3ab squared plus 3ab squared. And last but not least, over here, we have a to the 0. That cancels out. It becomes 1. So what you really have is 1 times b to the third. That's just a b to the third at the very end, plus b to the third. There's our answer for this problem, the binomial a plus b raised to the third power. And we didn't do it the long way. We did it using Pascal's triangle and the binomial expansion theorem. And you need to know how to be able to set that up. These numbers followed by the two parentheses with the maximum power of 3 being dropped from 3 to 2 to 1 on those first parentheses. And the second parenthesis going from a 0, increasing 1, 2, all the way to the 3. Now, if you would have had a 4 right here, then you'd have a 4, and then a 3, and then a 2, and then a 1, and so on, right? But you'd be using these numbers down here on the fourth power on Pascal's triangle. Anyhow, we got this answer. Yes, it took a long time because I was explaining this many things over and over and over again. There's our answer. Check out the answer that we got originally. there it is. Same exact answer. That was the picture that we took. So I think this is way better to do as opposed to actually distributing the binomial a plus b with itself 3 times. Now imagine if that were a 4 or a 5. This is still pretty easy because you have these numbers. Like if it were to the 5th power, you'd have 1 parenthesis plus 5 parenthesis plus 10 parenthesis and so on and so on. And in each of those parentheses, you put the a and the b right in there. So it's pretty amazing, this theorem, this truth about expanding binomials. Let's do one more, shall we? Let's go with the binomial 2x. Let's go minus I don't know, y. We'll go 2x minus y. Let's go to the 4th power. Now, if you tried, you could if you wanted to, right? The 2x minus y times 2x minus y times 2x minus y times 2x minus y. Distribute the binomial, but that's going to take forever. It's going to take like a whole page of work. So if you know this Pascal's triangle, and even if you don't know it, you could create it. Make a triangle of 1s, right? And then go 1 plus 1 is 2. Put 1s on the outside again. Add 2 plus 1 is 3. 2 plus 1 is 3. Put 1s on the outside again. 3 plus 1 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Put 1s on the outside again. It's really easy to create this triangle. And then after that, you just need to remember that anything to the power of 0 equals 1. And anything to the power of 1 will give you the coefficients 1 and 1 in front of your binomial, or in front of your terms. Power of 2 give you 3 terms, power of 3 give you 4 terms, power of 4 give you 4 terms, power of 5 give you 5 terms. So with that said, let's do this binomial to the 4th power. Okay, so we're going to be going to the 4th power, which means we have the 1, the 4, the 6, the 4, the 1, and we have 2 parentheses behind each of those coefficients. So there we have it. I know this looks long and disgusting. Imagine how long and disgusting this work would be if you actually did distribution and combining like terms. It would take a long time. So anyways, we're jumping straight to the answer using this binomial expansion theorem, of course involving Pascal's triangle. Now what's the maximum power here? The binomial has a power of 4. So on this first parenthesis, we're going to put the power of 4. Okay, put the power of 4 right there. And then if the first parenthesis has a power of 4, the second parenthesis is going to have the power of 0. Okay, and then the power of 4 is going to drop to 3 on this next first parenthesis on the second term. It's going to drop to a 3, and then to a 2, and then to a 1, and then to a 0, as this 0 increases by 1 on the second parenthesis of each term. Okay, so the 0 increases to a 1, increases to a 2, to a 3, and then to a 4. So we have the powers down. What belongs in the first parenthesis? The first term of your binomial, which happens to be 2x. So I'm going to put a 2x in every single first parenthesis. And then I'm going to plug in the second term of my binomial, which happens to be a minus y. I want to put a minus y on the second parenthesis, right here on all of them. And then after that, it's just a question of doing the work. Okay, now what do I mean by doing the work? Well, negative y to the 0 power. Anything to the 0 power is 1. So you could just scratch that out. Now, what is the work right here? We have 1 times 2 to the 4th, x to the 4th. Remember, when you have whenever you have a power of 4 with 2 times x, you distribute that 4 to each term. Or you could think of it as 2x times 2x times 2x times 2x, 4 times, right? So 2 to the 4th is really 16. Okay, so we have 16, and then x to the 4th is simply x to the 4th. And of course, the 1 times 16 is not going to change it. So here's our first term of this binomial expanded to the 4th power. Let's move on and do some more math right here. We have, what do we do first? Multiply 4 or exponents? Exponents always first. So we have 2 to the 3rd, x to the 3rd. 2 to the 3rd is 8, x to the 3rd is x to the 3rd. So what we really have here is 4 times 8x to the 3rd. And then over here, this power of 1 isn't going to change the negative y. So we really still have times negative y, or you could say negative 1y, okay? So what we really have as our second term is 4 times 8, which is 32, times negative 1, which is going to be negative 32. And of course, with that, x to the 3rd and y, Okay, so our first part of our answer, 16x to the fourth. Second term, negative 32x to the third y. The next part, let's distribute 2 squared. 2 to the second power is 4x to the second. So what we really have here, you know what, we might as well zoom in a bit. So zoom in right here. So when I do this work, let me do this in green so you can see it. 2 squared is 4, x to the second, okay? Now think about this. Right here we have a negative y to the second power. Negative times a negative is a positive. So what we really have is just a positive y squared, no more minus sign. And then of course we have this times 6 out in the front. So this next term is actually going to be plus 6 times 4 is 24 x squared y squared. Okay, let's move on to the next term over here. It's going to be kind of weird because the ink ends up coming out fine and over here it's bold. Anyways, let's do this next one over here. Let's distribute the 1, nothing changes, so you really have 4 times 2x. What is that really? That's a positive 8x. But then you have a negative to the third power. Negative times a negative times a negative ends up being negative. So you really do have a negative 1 times negative 1 times y to the third. Okay. So again, I hope you understand that any odd power of a base that's negative ends up being negative, right? So I could have put just negative y to the third, but I want you guys to clearly see that we're going to be multiplying this 8 that came from 4 times 2. We're going to get that 8 and multiply it by negative 1, giving us the next term to be negative 8xy to the third. Again, the x, the y to the third, the negative 1 times 8 gave us a negative 8, right? Moving on to the next term. And we are almost done here. Last term. It's easy. The first one and the last one are easy. Anything to the 0 power is 1. So what we really have is 1 times 1 times, what is a negative y to the fourth power? Negative times negative times negative times fourth. It's going to be a positive. So you're going to have a plus y to the fourth. Ladies and gentlemen, this is our answer. Check it out. So this binomial to the fourth power, that is this answer right here. Pretty amazing. You know what? If you're bored, go ahead and try to do this the long way with distributed property. You'll see how ridiculous it is. Even though this looks long, if you try to expand this, man, you're going to have a whole page worth of work. But anyway, this is the answer that you'll get, even if you did expand it the long, boring way. Okay, so let's get this theorem down. Let's understand how to create Pascal's triangle. And guess what, guys? This is the last section on chapter 10. We're done. We are done.